Our project is an in vitro surgical cranium model for brain mass removal by Alfredo, Mahmoud, Arnav, Cassie, and Melissa. Traditionally, neurosurgeons remove brain masses by opening the skull through a craniotomy to ensure they can access the tumor and remove as much of it as possible. They are very high-risk procedures, and based on our research, they typically take about 4 hours. On average, neurosurgeons can be expected to perform about 223 cases each year, and over 75% are brain and spinal tumor removal surgeries. Our training methods include cadaver dissections, which are extremely expensive, in vivo animal testing, which are treated as unethical, and engineered models, which are fairly new. To improve the lo-fi prototype from our previous model, we 3D printed personalized molds with PLA materials that would encapsulate a ready-to-use brain mold that would be purchased online. To construct the skin and bone tissue, we use positive and negative molding methods to compress the material to the desired shape. Figure 3D represents the molding technique used for the skull, where a paper mache was compressed. A similar procedure performed for the skin tissue, compressing the dragon skin, a silicone rubber material. Figure 4A and 4B represent the fully casted skull and skin parameters, and brain was constructed in layers by pouring the gelatin midway into the mold and letting it cool before we placed a maraschino cherry in a specific location to represent the tumor. It was then covered with more gelatin to solidify the embedded mass. Our tests focus on verifying statistically significant improvements of 2 parameters, mass removal accuracy and time duration. Our preliminary results showed a 60% increase in mass removal accuracy and a 24% decrease in time duration. The results indicated 0.12 gram increase in accuracy per attempt and a 1.3417 minute decrease in time per attempt. However, the number of attempts and the number of users are not adequate to draw any conclusions. More tests, ideally with medical students, are needed to accurately test the efficacy of our model. For our future models, we want to implement a model tumor in order to mimic a more intricate brain surgical procedure. We also want to work on our protocol so that it accurately follows the actual surgical procedure from start to end. Currently, our tools are good enough to meet the requirements of a current protocol, but as we improve our design, we will need more complex tools. However, our current model is designed to scale and the materials are carefully selected to mimic a human brain. We still think that it can be improved and developed to be consistent.